everyone, in this video we are going to see about what is thermal runaway. We shall see the basic concept and we shall move on further to thermal resistance and thermal stability. A thermal runaway is the maximum average power, that is PD max, which a transistor can dissipate depends upon the transistor construction. If we see the dissipation of power, it will be ranging from milliwatt to 200 watts. So, the power dissipation will happen in the collector base junction of a transistor. You have to keep this in mind that the power dissipation will happen in the collector base junction of the transistor. If we consider a silicon transistor, the temperature due to this power dissipation will increase in the collector base junction. So, the range is from 150 degrees Celsius to 225 degrees Celsius. If we take a germanium transistor, the temperature range is from 60 degree to 100 degrees Celsius. At the collector base junction, that is CB junction, temperature rises due to two reasons, that is due to rise in ambient temperature and the other one is due to self-heating because of the power dissipation. We must note that the excess heating may even burn the transistor or it may destroy the transistor. This concept is called as thermal runaway of a transistor. Thermal resistance and thermal stability must be considered to avoid the thermal runaway of the transistor. So, let us see about the thermal resistance first. The thermal resistance is the steady state temperature rise at the collector junction, which is proportional to the power dissipated at the junction. So, we can write the expression as dou T is equal to T suffix j minus Ta, that is equal to theta Pd, which is Tj is junction temperature in degrees Celsius, Ta is ambient temperature in degrees Celsius and the Pd is the power dissipated in the collector base junction and the theta is the constant of proportionality. This must be noted properly because theta is the one which is going to determine the actual thermal resistance of the transistor. So, if we consider the graph, the observation should be made like theta varies from 0.2 degrees Celsius per watt for a high power transistor with an efficient heat sink to 1000 degrees Celsius per watt for low power transistor which is not having the proper heat sink. So, the maximum collector power PC allowed for safety operation is to be 25 degrees Celsius. So, if we see the graph, the power will decrease when temperature increases. This is the concept of thermal resistance. Now, we shall move on to the condition for thermal stability. The required condition to avoid thermal runaway is that the rate at which heat is released at the collector junction must not exceed the rate at which the heat can be dissipated. So, if we take dou Pc by dou Tj, which must be less than dou Pd by dou Tj, which is nothing but the collector base junction temperature should not exceed, that is it must be less than the power dissipated. Okay. So, if we know that we already discussed like dou T is equal to Tj minus Ta, which is equal to theta Pd. So, if we differentiate that equation, we get 1, that is we have to differentiate with respect to Tj. So, we get 1 for Tj and which is equal to theta dou Pd by dou Tj. So, from this we can get dou Pd by dou Tj is equal to 1 by theta, which is taken as third equation. When we substitute this third equation in the first, we get dou Pc by dou Tj must be less than 1 by theta, that is it must be less than the inverse of constant of proportionality. This condition must be satisfied to prevent thermal runaway. How we are going to achieve this? This can be achieved by proper designing of biasing circuit. Now, let us take an example and analyze. We are going to take an example like voltage divider bias circuit. We are going to analyze it. This is a voltage divider bias circuit and we know that Pc is heat generated at collector junction and Pc is DC power input minus the power loss as I square R in RC and RE, which is the power loss is nothing but what is the power dissipated in the collector base junction. So we can take like why we are saying as DC power input is the circuit will be operated only by the power input. There is no input given to the circuit. The voltage which is given as DC will be the input for the voltage divider bias. So therefore PC is equal to VCC into IC, that is the DC power input, minus the power loss is IC square RC plus IE square RE. If we consider like collector current is equal to emitter current, that is IE is equal to IC, we can get PC is equal to VCC into IC minus IC square, we are going to take it as common and we write RC plus RE. Differentiating the above equation with respect to IC, we get dou PC by dou IC. We are going to differentiate and we get like VCC minus, we differentiate IC square, we get 2IC into RC plus RE. We take this as first equation. We already know that dou PC by dou Tj is less than 1 by theta. So if we multiply numerator and denominator by dou IC, we get dou PC by dou IC into dou IC by dou Tj, which is less than 1 by theta. We take this as second equation. And also we must note that dou IC by dou Tj is equal to S into dou IC naught by dou Tj plus S dash dou VBE by dou Tj plus S double dash dou beta by dou Tj. While doing analysis for thermal runaway, IC naught dominates. So we can reduce the above equation as dou IC by dou Tj is equal to S into dou IC naught by dou Tj, because the VBE and beta will be reduced. Since IC naught is the dominating current, we get this equation. So by doing the reverse saturation current for both Si and Ge, that is silicon and germanium, increases about 7% per degree Celsius. So we can tell like it is equal to 0.07 IC naught. Hence we get dou IC by dou Tj is equal to S into 0.07 IC naught. By substituting this third equation and the first equation in equation 2, we get VCC minus 2IC into RC plus RE into S into 0.07 IC naught, which is less than 1 by theta. This is the fourth equation. So we can see like S, theta and IC naught are positive. We see that inequality in equation 4. So we need to satisfy the equation to get VCC minus 2IC into RC plus RE as negative. To do this, we must take VCC as less than 2IC into RC plus RE. So if we take the 2 to the denominator, VCC by 2 less than IC into RC plus RE. Applying KVL for the collector circuit in the voltage divider bias, we get VC is equal to VCC minus IC into RE plus RE. This we can apply using the voltage law. Okay. Therefore, we can assume like collector current is equal to emitter current. We get IC into RE plus RC is equal to VCC minus VCE. Substituting this IC into RC plus RE, which is less than VCC by 2, we get VCC by 2 less than VCC minus VE. So VCE is less than VCC minus VCC by 2. So we get the collector emitter voltage as VCC by 2. From this we can say the stability is ensured. We must also note that in a transformer coupled circuit, RE and RC value will be very less and VCE will be approximately equal to VCC. It is necessary to design transformer coupled circuit with stability factor close to 1 to avoid thermal runaway. Hope you have understood the concept of thermal resistivity and the thermal stability. With this, we can avoid the thermal runaway of a transistor. Thank you.